Hi, my name is Dominik, and I'd like to present our work on scene explanation through verification of stable object poses. For a human interacting with a robotic housemate, communicating in terms of objects comes natural, and the robot's notion of the environment is easily visualized. Given object models and their respective poses, a robot is enabled to plan its movements and interactions within complex scenes. However, the ever-changing set of objects making up the environment poses a problem, as handling novel object instances often requires expensive data acquisition. In real-world scenarios, objects tend to rest on a locally planar surface and are observed in a limited set of physically stable poses. The geometry of both the environment and the object, as well as their physical interaction, thus heavily restricts the space of admissible object poses. Building on this observation, we propose an object pose estimation approach that requires only approximate 3D models, enabling a robot to quickly adapt to novel object instances. Assume an object is placed on an infinitely large plane. A convex object may rest on any set of points on its boundary. Non-convex objects may only rest on the convex subset of their boundary. For meshes, this boundary is piecewise continuous. Each rest pose is described by a hyperplane up to in-plane rotation and in-plane translation. The intersection of these hyperplanes is equivalent to the convex hull of the object. Therefore, the object model can be of arbitrary precision as long as the convex hull remains the same. These geometric considerations also apply to finite planes if all faces of the convex hull lie within the plane's boundary. Not only the object's geometry, but also its physical properties restrict the admissible poses. To determine physically stable poses, the object is initialized in a physics simulation in uniformly sampled rotation intervals. Each simulation is progressed until a stable pose is reached. As this process yields many similar poses, we cluster them to find a small set of representative stable poses per object. To compute an object pose estimate using these stable poses, we have to estimate the in-plane rotation and in-plane translation from the observation. The pose estimate should minimize the discrepancy between the observation of the object and the rendering under the estimated pose. We achieve this by first taking an initial guess at the in-plane translation using the observed depth, generating a set of in-plane rotation hypotheses for each stable pose, adapting the translation estimate per rotation hypothesis, and finally, selecting the estimate with the lowest discrepancy based on a rendering-based verification score. The resulting approach only depends on approximate, non-textured object meshes for pose estimation in cases where a sufficiently large supporting plane can be assumed. We compare our approach against three methods using either synthetic data or 3D models for training. As shown, our approach provides better initial pose estimates than the related methods. Also, using a baseline ICP implementation, we are able to outperform the competing methods using refinement on line mode. In addition, we evaluate the impact of mesh quality on accuracy. An example of 4 evaluated approximations is shown. The results show that our approach is able to perform well even with highly decimated meshes. The simulation produces similar pose estimates, and the verification is still able to fit approximate meshes to the observation. In future work, we plan to investigate means to determine the required object models during robotic exploration of a scene. Another open point is the preservation of physical plausibility after additional pose refinement. In summary, we presented an approach to object pose estimation that computes a set of physically stable poses using approximate 3D models and physics simulation. Using rendering-based verification, we are able to determine which pose hypothesis best fits the observed scene. The resulting approach is able to achieve state-of-the-art accuracy on the line mode and occluded datasets.